Okay, so before we get started on experimental probability, we'll warm up by expressing some fractions as percentages. We should know how to do this from previous courses. So if we have 1 divided by 5 or 1 over 5, we can plug that into our calculator and find it equals 0.2. Well, I can take that and multiply it by 100%. 0.2 times 100 is 20%. We can perform those same steps on 3 divided by 7. So if I plug 3 over 7 into my calculator, I find it equals 0.43. Again, I can multiply that by 100%. So 3 over 7 is the same, represents the same number as 43%. Now, let's see here, our key terms. When we're talking about experimental probability, note that this is different from the usual way you're used to using probability, which is theoretical probability. Theoretical probability we'll go over next. Probability. We'll go over next. Statistics lesson. First, we'll cover the experimental stuff today. So before we talk about outcome, we'll talk about what actually is an experiment. Experiment is an observation of an action, meaning you're watching something happen. It's a little bit different than from an experiment, say, in science as you're used to doing. They take a little more planning to do a science experiment, but you'll see what we mean here in a moment. Now, an outcome is a possible result of an experiment. So for example, let's say our experiment is rolling a die. If we roll a die, it can come up a 1 or a 2 or a 3 or a 4. We can roll 5 or 6. Those are all possible outcomes of the experiment. A trial is one round of a probability experiment. So when we're working with experimental probability, we'll always be performing an experiment more than once. Sometimes that means we're rolling a die once or twice or 3 times or 50 times or 100 times. And we'll note that the more trials we have, the more accurate our experimental probability can predict things. Now, an event is a set of outcomes with the same result. Often, event and outcome mean the same. They are the same thing, but they definitely don't mean the same thing. And in some examples, they'll be a little bit different. You'll see what we mean later when we go through the examples. Experimental probability, as I said before, it is different from theoretical probability. It's determined by the results of an experiment. And that's important. That's determined by the results. That's what makes it different from theoretical probability in a way. So when we represent experimental probability mathematically, we'll write out a capital P with a small e. So experimental probability. Write that a little bit neater here. And we can calculate that by taking the number of successful trials. You'll see what we mean there in a moment. Successful trials, and we can divide that by the total number of trials. So let's just jump right into it and calculate some experimental probabilities. If we have here, we have Jojo flipping a coin 12 times in a row. That's important that she flips it 12 times. If 8 of these flips turn up heads, then what's the experimental probability of getting heads? Well, from our formula above, the experimental probability of getting heads. So this is how we'll write it. We'll write experimental probability as above, and then in brackets, we'll talk about the actual outcome, or the actual event that we're dealing with here. So the experimental probability of getting heads equals the number of successful trials. So in this case, that's the number of times that you actually did flip up a heads. Number of successful trials, in this case is the number of heads, divided by the total number of trials, and seeing as she flipped the coin 12 times in a row, that's where we'll get that number. So the number of heads is 8, number of trials is 12. If I put that into my calculator, I get 0.66 repeated. If, as above, I want to show that as a percentage, then I can multiply that by 100%, which is 67%. Now, what's the experimental probability of getting tails? Well, this time we don't quite have all of the information given to us, but we can figure that out. So the experimental probability of getting tails is the number of tails divided by the number of trials. Well, we have the same total number of trials, that's just 12. We don't have is the number of tails. We can calculate that though, because when we flip a coin, we know that the only possible outcomes are heads or tails. So the number of tails is all of the outcomes that were not heads. So our total number of outcomes, that's our total number of trials, minus the number of heads. The number of trials is 12, our number of heads is 8, 12 minus 8 is 4, meaning number of tails is 4. If I put that into my calculator, I get 0.33. I can express that as a percentage by multiplying it by 100%, equals 33%. Perfect. Now, one thing to note, if you take this 67% and the 33%, 67% plus 33%, if I plug those into my calculator, it equals 100%. And that makes sense because the only possible outcomes, as we said, are turning up heads and turning up tails. So all the time, we're either going to turn up heads or turn up tails. All the time is 100%. Now, Pippi's rolling a 6-sided die, 6 sides, several times, and recording the data in the table below. Note, we're not told how many times, it's just several. What's the total number of rolls? We calculate that. We see our table here. In our left column, we have the side of the die. We roll a 1 or a 2 or a 3 or 4 or 5 or 6. And on the right side, we have the frequencies. That's the number of times that we roll those numbers. So the total number of rolls is the number of times we roll a 1 plus the number of times we roll a 2 plus the number of times we roll a 3, all added together. The number of rolls will be our number of trials, and that's 2 plus 3 plus the number of times we roll a 3, which is 4, plus 3 plus 5 plus 3. If I plug that into my calculator, then I find it equals 20. Perfect. I can use that number to calculate my experimental probability. So my experimental probability, this time it's asking me of rolling a 3, equals the number of times we rolled a 3, that's the number of successful trials, divided by the total number of trials, which we calculated above to be 20. number of times we rolled a 3, we can take that right from our table here. 1, 2, 3, number of times we rolled it is 4. So if I plug that into my calculator, 4 divided by 20 equals 0.2. I can multiply that by 100%, and it's 20%. So the experimental probability of rolling a 3 was 20%. Now, what percentage of the rolls resulted in the die showing less than 3? So that's interesting. Which numbers here are less than 3? 1 is less than 3, 2 is less than 3, 3 is not less than 3, 3 is equal to 3, so that does not fall into this category here, nor does 4, 5, or 6. So the percentage of the rolls, what we're asking for, when we see this, is the experimental probability. Experimental probability, this time it's not of 3, but it's of less than 3, equals the number of successful trials, which in this case is the number of times we roll a 1, or the number of times we roll a 2. So we're going to add those together, divided by the total number of trials. Well, our total number of trials hasn't changed from above what we calculated. It's 20. Number of times we roll a 1 is twice. Oops, not multiplying, we're adding here. And the number of times we rolled a 2 was 3. So the experimental probability of rolling less than a 3 would be 2 plus 3. We're going to put that, we'll always put that in brackets on the top if it's more than one thing. And we're going to calculate this. Now remember, when we're calculating this, we need to calculate our brackets first. So let's just fix that here. We need to calculate our brackets first. So 2 plus 3 is 5 divided by 20. If I plug 5 divided by 20 into my calculator, I get 0.25. And if I want to show that as a percentage, that's 25%. So look here, we have 2 more examples to go over. Here a coin is tossed 50 times. The experimental probability of the coin turning up heads was 4 over 10. How many times did the coin turn up heads? So here we have a different kind of question, but we'll solve it using the same formula. The only difference is we have a different unknown. Previously our unknown was the experimental probability, but this time we're given that. So we'll write down our formula first. The experimental probability of heads equals the number of successful trials, which is the number of heads, divided by the total number of trials. Well, the number of heads is unknown. That's what we're trying to figure out. How many times did the coin turn up heads? We'll write that in as an X. And the number of trials we know is 50 times, so we're given that. Now the experimental probability of rolling heads, again, we're given that this time. It's 4 over 10. Now, this left side here, I can plug that into my calculator right away. We can always do that if I have a number divided by a number. So 4 over 10 into my calculator is 4 divided by 10, that's 0.4, equals x over 50. And my goal is to isolate for this x. Right now it's being divided by 50, so I need to multiply it by 50. And I need to multiply the left side by 50 then. These can cancel out, leaving me with x equals, plug this into my calculator, 50 times 0.4, that equals 20. So therefore, the coin, because it's a word problem, we'll answer with a sentence here. Therefore, the coin turned, turned up heads 20 times. Now, how many times did the coin turn up tails? We could go through all of this just like last time, but rather, let's take a look at what we did previously. Remember, to calculate the number of times something turned up tails, if those are the only two options, then we can take our total number. So the number of times it turned up tails equals the total number of trials minus the number of heads. Well, I know there are 50 trials because that's given to us in the problem, and the number of heads we calculated last time, that's 20. 50 minus 20, you can use a calculator or do it in your head, that's 30. So therefore, the coin turned up tails 30 times. And our final question here, Maxie has a bag full of apples and oranges. So those are the only two things in the bag. Maxie randomly pulls out 30 pieces of fruit. That's going to be important. And if the experimental probability of pulling out an apple was 2 over 3, then how many apples did Maxie pull from the bag? Again, we're going to work with the same formula. So the experimental probability of apples equals number of successful trials, and that means the number of times that we pulled fruit out that she pulled out an apple. We're not the number of, that tells us the number of apples, and that's divided by the total number of trials. Here she randomly pulls out 30 pieces of fruit, so that piece of information is important because that's our number of trials. That's the number of trials is 30. Now the number of apples, we're not sure. That's what we're trying to figure out, how many apples. So we can just represent that by writing in an X. And our experimental probability of pulling out an apple, we are given that. It's 2 over 3. I can put that into my calculator right away, 2 over 3. 2 divided by 3 is 0.66 repeated equals X over 30. And what I need to do is, again, we're isolating for X because that's what we're trying to find. So right now it's being divided by 30, so I will need to multiply it by 30. If I do it to the right, I need to do it to the left. These cancel out, bringing me 30 times 0.66, which is 20, if I put that into my calculator. So therefore, Maxie pulled 20 apples from the bag. It's always a great idea with our therefore statements here that we're writing at the end of the word problem. It's always a great idea to use the same wording as was in the question. How many apples did Maxie pull from the bag? Maxie pulled 20 apples from the bag. And we're going to look at a similar question here. So how many oranges did Maxie pull from the bag? Well, this time we don't need to use this this formula here. I mean, we're not given the experimental probability of pulling out an orange. We're only given that for apples. But what we do know is that she can only pull apples or oranges from the bag, meaning if she pulled out 30 pieces of fruit, number of oranges is the total number of fruits, which is the number of trials, minus the number of apples. Well, the number of trials, that's the number of fruits, is 30, minus the number of apples, which is 20. Oops, 20. 30 minus 20, you can use a calculator, do that in my head, that equals 10. So therefore, Maxie pulled 10 oranges from the bag. And what's the experimental probability expressed as a percentage of pulling out an orange? Well, I've done this before, the experimental probability of pulling out an orange equals the number of oranges divided by the number of trials. And the number of oranges here is 10. I calculated that in the previous question in part B. And the number of trials is 30. That's the total number of fruits pulled from the bag. If I put that into my calculator, I get 0.33 repeated. And I can multiply that by 100% to find the experimental probability of pulling out an orange is 33%.